Obrigado, é um prazer para mim falar aqui. Havia muito tempo. Don't worry, I will give the conference in English. Just thank the people and thank for the invitation. And it's a great pleasure for me to be here again at IMPA, where the first time was, better forget maybe, something like 1980. And it's also a pleasure to speak about a topic where one step was done here at IMPA in 85, and in particular because of conversation with Otto Spur, who is still here at IMPA, and which helped to understand the topic. So, let's see if I can master this technology. The topic is curvature near an isolated singular point of a polynomial. So, I will cheat during the whole conference, making real pictures and thinking of complex objects. So you have the origin, which is an isolated singular point, and where f is a polynomial, and we look at levels for a small lambda, and the question is, okay, what's going on? So all that is in a small ball, which I draw very big, but it's just the ball of radius epsilon. And when you approach a singular level, what happens? And then first I should just say two words about complex curves. C contained in C square. What does that mean? So it's a complex curve. It means it's a surface contained in some special R4. And IMPA has a wonderful technology, but not yet four-dimensional blackboard. So I need to draw on a blackboard or to project slides showing objects which are plane, but maybe representing surfaces in R3. So here is exactly the projection on some R3 of this object, the intersection of f equals lambda with a small ball. And I will show a few more. A few more projections, but of the same objects, just to show that this is not so easy to visualize a complex curve. And one way is just dealing with a lot of projections. And what I did is a sort of global. I just took planes, real planes, in, I took a real three-dimensional space in C2, and I project on it. And that's the type of picture one can get. One more observation about complex curves. They are very special surfaces. And in particular, they have a local property, which is the following. Here is the surface, so now I do my best not to draw it. And the tangent plane, which is a tangent complex line. And now let's choose one normal vector, m theta, and rotate this normal vector to obtain a one-parameter family of three-dimensional real space. Then the projection will look the following. The curvature at the point, say, x, is always negative. And when you change the normal vector, it just rotates. That means somehow the curvature is the same, but just the picture rotates when you look at those different projections. Okay. So probably this was this transparent. No. And now one more tool which I will use in this exposition. It's the notion of polar curve associated to a foliation. So it may be a foliation of C2 by curves, complex curves, and of course I cheat and I draw only a foliation of R2 by real curves. And you see this foliation. And the polar curve is just defined using looking on each leaf at the critical point of the projection, the orthogonal projection on this line. And you can see that in general it gives a curve which may be sometimes tangent to the foliation when the tangent direction is just an inflection of the leaf of the foliation where you are looking at. So I should be able to point and show it here, for example, or here. And it may also be a singular curve. Of course, if you look at different projections on different lines, give different polar curves. And now let's come back to our topic. And again, cheating with real pictures. Here is a more realistic than the first one I did on the blackboard, because done with a computer, and all that was done not by me, but by Jean-Claude Siffre, with whom I'm doing this work, which is still in progress. So you have the singular curve. You have one f equals lambda, of course, we didn't draw all the levels because then the picture would be confused. And you have, oh, no, I didn't want to do that. I wanted to point. You have a bunch of curves here which have the same tangent at the origin as the polynomial x3 minus 2 equals 0, and which are polar curves. So let me try to draw what is not on this slide. Here I had one level, but you should imagine many others. And then we can look at polar curves for projection on many directions. If you take the horizontal directions, you see something like that. Okay. And if you tilt the direction of projection, you get another polar curve. And in my examples, all these polar curves are just tangent at the origin, and in fact, we'll see soon that they are all parabolas. And now, let's zoom at the interesting region. And it seems that there is a shape of what we obtain by zooming. So this is another example of the same situation, but not with a level of a polynomial, but with just a foliation, which I describe using a one form. And the foliation is, the plane field is just the kernel of omega. This is the example of a saddle node. And I just zoom at a place which looks interesting, where all these polar curves, but then I should define a polar curve for a foliation using omega, and this is very easy. It's just taking omega over vector equal 0. And to give a notation, I will call this curve gamma AB. So that's another example of this zooming procedure and giving some limit shape, which we will see more precisely later. So now I want to look at the geometry of this level after zooming. And I want a procedure to obtain the result, to first know where to zoom at, and second, to see if there is some limit shape if I take a leaf of the foliations closer and closer to the singular point, and if I zoom at the proper scale. So here are some explanation of how to do, what it means to zoom at. To zoom at means just a change of variable, and here we are zooming, the lens is centered at the point x0, 0. In the example, the x-axis is the tangent line, and moreover, it's singular in some sense, because among tangent lines to a singular curve, well, there may be a few, because the curve is not necessarily irreducible. You can distinguish between two conditions. Do I have something? Yes. You have a tangent cone. Just you get it looking at df, but you can have just the condition of df at 0 of a direction, say a, b, equals 0. And you can have also the case where when you look here, example, f equal x3 minus y2, when you look at df at the origin, you get a 3x squared dx plus minus 2y dy, and this df at the origin is identically 0, not only using at some direction. And this fact, of course, is necessary to understand what occurs. And to get the tangent cone for f equals 0, you see that we have just to look at the terms of lowest degree of f. So low df equals minus y squared. But still you see this square. And if you look at df, the low of f, at 0, this is just 0. We will see why this is important when we rise the dimension. Anyway, when we zoom like that, that is, we make this change of variable at the point x0 on the x-axis, we have to adjust the strength of this length. And to do that, I will use a very classical construction, which is Newton polygon. Newton polygon, they were used to get a parametrization of a singular curve. Where is white? Maybe I should say Newton-Puiseux method. The polygon is Newton, and then the use of it was sort of, the details were filled by Puiseux, is the following. Taking a two-variable polygon, should be a coefficient, one can plot all the exponents. One more here, a few more, and take the convex hull of the region of the plane I am drawing at each point which correspond to an exponent. I associate a quadrant and then take the convex hull of the whole stuff, and I get a polygon. And this was a very simple and brilliant idea of Newton, saying, okay, maybe it's difficult to try to write for a branch of a curve given by this equation. We want something like that, where phi is not a theory with integer exponents, because this will not allow singularities, but something like a I x, and we use some exponent like that. And the idea is try to get that by induction. So try to get first the first term here. So one way to get it is just to look at the side of the polygon, saying, okay, we cannot guess what's the solution of this equation, but let's sort two or a few terms and consider they are the most important and eliminate them. So what does that mean? That means that here you have the example of the picture for, this is just a trivial case for a parabola. So we are starting with f equals 0 for f equals x3 minus y2. df will be 3x2 dx plus 2y dy. So then it's not necessary to look at the polygon to guess what is the solution when you look at df of AB equals 0, which is one of the equation of one of the polar curves. But you know that you get exactly a relation between, you see those two terms, and you see that the slope, which is minus 1/2, will give the exponent when you start the computation. But I am not exactly interested in this Newton polygon, but another, and that's why I call it Newton length polygon, because I want to find the proper change of variable. So now I have df of I choose a point, x0, and I choose a ratio, rho, and let's say x1, and the same ratio, which is the strength of the length, rho y2. And I would like to know what the right relation between rho and x0 close to 0, and rho the strength of the length. And then what I need to do is to have a Newton cloud and a Newton polygon, but in these new variables, x0 and rho and x1 and y1 are just in the coefficient of this polygon. And that's why I get 2 extra points when I just substitute in the equation here this change of variable. But I have the same vertices of the Newton polygon. And then I know that this gives immediately the fact that rho should be x0 squared. And when I do that, so this is when I do that, maybe let's get back to what I'm doing is exactly what you see. And when I do that, I can see that all the terms which don't involve a power of x0 will give the equation of a parabola. So this is not such a surprise. So there is an idea behind that. Remember that I claim that in many cases the polar curves are also tangent to the singular curve. And in the case of the example, these polar curves are just parabolas, and changing AB will just change the coefficient. And we are looking very close to the origin. What's going on? And when we enlarge a family of curves which are tangent, what do you see? Almost parallel lines. So we have to think that what we get in the limit, I'll keep the colors which are here, is a bunch of parallel lines, and polar curve means that the tangent direction to the foliation is given. So along such a line, we know what the tangent to the foliation should be. For example, I'm drawing just something which looks like what is there. And then we see that just this data gives a limit foliation. We have this line field which should appear. No, it's this way. This is another example for another polynomial of what can be done. Okay. And just to show that we don't see only parabolas, in this case, it's a cubic curve which will appear for this f. And the the interest of this result, where you see f has parameter in it, is to show that, in fact, when we look at the neighborhood of an isolated singularity of a polynomial, we can get any limit shape we want. Any polynomial can appear when you just zoom at the proper scale and look at the place where the geometry of the surface is really concentrated. So this is an example. The first one was found by Cifre some years ago, 30 at least, in the 80s. And also this was worked on by a student of mine, Patrick Rouillet, who defended the thesis in 92. One more example, and this is second step. What does that mean? For those who know how to get the Puiseux expansion of a parametrization of a branch of an algebraic curve here, they know that one step is not enough. What I've done was just the first step. But sometimes we cannot just stop, and we have to look for other terms in this expansion. And for that, we have to repeat the change of variable procedure. And of course, the same thing will have to be done when you want to look carefully at what happens. And let me be a little bit more precise here. And then I should quote Michel Merle, who studied systematically not just some examples and the polar curves, but the general case and how all these polar curves are in space. And what he proved is the following. You have the singular curve, f equals 0, and the polar curves have different branches, so maybe I should be more artistic and use different colors for different slopes. And there may be another bunch here. And there may be some very special polar curves gamma AB when AB is tangent to gamma AB at the origin. And these curves may be just inside the pack of the generic ones, or really separated. This is more Rouillet than Merle. And then I will explain what Merle's contribution is. And also, one can look at the contact of this pack of polar curves, how close it is to the level f equals 0. So let's zoom a little bit here and take just one of the white curves and f equals 0. What I mean is I just want to, I take just one, to have an idea depending on the position of a point x0 to this transverse distance between a polar curve and the curve. And what Mel shows is that when you play the induction or another procedure which is called blowing up, you see the polar curves which sort of stick to f equals 0. And at some moment, you can see they got apart. So that's a way to filter the procedure and to say, okay, we have to wait doing the induction simultaneously when the Puiseux series of f equals 0 and of a polar curve have a coefficient which is different. And that follows this Newton Puiseux induction. And now when doing and I call Newton length induction, the same thing, but with a change of variable which correspond to zooming. In fact, it just goes exactly parallelly. We have the same Newton polygons, or at least I think we have exactly the same, and this is something which I should say is a conjecture, or rather we think we prove it with Jean-Claude Siffre. That is, same induction, Newton length will therefore have to end at some moment. And what we are doing, in fact, is the following. We are zooming. Let's take x0 on the other side. And when we do so, either we are very lucky, first step we see the shape, either we are not. So I enlarge the ball. And if we are not, what we see is just a few lines parallel. And let me explain why you see that. One has to cheat in all possible ways, with dimensions or with codimensions. So look at the saddle point. Like that. And now, let's suppose we are not at the right scale. Still comes from some, let's say, some polynomial equation. But we see it from very far away. What will happen? This stuff will look completely flat. When we are here, the curvature, when you look from more and more the distance which is bigger and bigger, will just be shrink, and the two curvature will be shrink. But we have to remember it's a complex surface in C2. So then, what you see is something, it's okay, should do something like that. okay, it's difficult to draw complex, but everything is shrinked, and essentially you have something here, and you see a line corresponding to just the asymptote of this polygon. So now, when we are at this situation, it's clear we have to zoom again. And that explains how we get this second polygons. Opa. So now this helps to understand what occurs for curves, but this was already, some partial results were known before, and people were more interested in the total curvature near a singularity, or even trying to split in different smaller pieces and just zooming to get the precise shape. But there is a case where much less is known, is complex surfaces in C3, or let's say complex surfaces of equation f of x, y, z equals lambda, f a polynomial, or more generally, a foliation where the coefficients are polynomials. And then it's more difficult, but we can try to understand what's going on. And then I should go back to my try to explain why when you take the graph of a polygon from the distance, you just see a line. Here, we look at the graph of a surface from the distance. And let's do that in R3 to try to understand what occurs. And first, let's do that for just a piece of cylinder. From far away. Suppose the asymptotic, the tangent plane has a limit, which is vertical. From far away, what you see is just something which looks like a half plane, but you have two sheets if it's a cylinder like on my picture. And now you may have also the situation where it's not exactly a cylinder, but one of the curvatures is much bigger than the other, and the ratio goes to infinity. Then with the length of the right strength, we see something like that. And this object has naturally some Gauss curvature as a surface does, because we can think of the normal vector going from this direction. When you go there, just flips. But it's a limit section is a limit of something like that, where you have your half turn. So now let's see what are you, and okay, boundary of pancakes. Wet barracks was just this situation. Some who the people who did camping after the rain know that this happens. And then you understand that this type of picture shows that there should be some curvature, some Gauss curvature concentrated on this edge. Okay. So now let's start with examples in for surfaces in C3. And okay. Here it's somehow not a serious example because it's just obtained from the first singularity I considered and by rotating. And of course, again, it's a real picture which pretends to sum up present the complex reality. The point is that computations are easy with complex numbers, and pictures are doable with real numbers. So we should do both and try to make the two viewpoints match. So this is the example. When you look at df, you can again look at the Newton polygon, and then what you see as a limit, remember the picture I did before, what you have naturally at the limit is a differential equation, or differential equations in that case, which will just tell you exactly what you want. That is, that you will get a solution which is a paraboloid of revolution, which is this limit shape you get by zooming at the scale which is given, which is given, just choosing this coefficient here. And it's obtained by looking at the Newton length polygon. Remark, if you take f of x, y, z equals 0, if you play the same trick of Newton, you get a polyhedron. Because the Newton cloud is three-dimensional, and then, okay, I should put, let's say, very simple example. I get some two-dimensional object. But if I just look for a length, and I know where I should center it, so let's say centered at x0, 0, 0, for example, I just have two variables left, the strength of the length and the distance of the point where I'm looking at to the origin. And that's why, whatever the dimension is, the Newton length polygon will always make sense and be as tractable as in the case of curves. Okay, another example. All examples show a singular surface and a closed, non-singular level to try to see what we want to look at. And here is another example where you should see this piece. The black is the closed level, the f equals lambda, and the light gray is a singular level, and something seems to occur there. Here is another example, and I will finish trying to understand what occurs with this example. And now we don't have a clean theory about what goes on, but we are trying to just look at some simulation and then play the same game and see where curvature and some interesting geometry may occur. And here you see the sort of bag when you look at the f equals lambda, where there is something here, there is something here, here, and it seems that to be very thin, to be folded. So let's see what happens when we try to compute. So to compute where, first you have the x-axis, and then we see, where is it? Yes, it's here. Just differential equation which when integrating give parabolas. Yes, you have a first degree term. When you integrate, you get a z1 square. Okay. So the x-axis, the origin is somewhere here, and the x-axis should go through. And you have the z square. But all the direction of the xy plane are interesting directions, in the sense I roughly did not explain at the beginning. So let's see what happens when you look at a point on the y-axis. So where is the solution? Then maybe we look at the picture. So you're here, you are here in this, and you see it really looks like almost an inflection, so it seems to confirm. And if you look at the differential equation, when you integrate that, you get a cubic term. And now I put the length, yes, that's the length at a point 0, y 0, 0. And we can also try to find other points which are not on an axis or on a singular tangent. And we see that we can see other shapes, limit shapes. And in that case, which is very simple, because you just have one different exponent for each variable, we hope we got everything. Now, we should be sure, and that's a difficulty we haven't overcome yet, is doing the right thing there, because we want to restrict to planes, but which planes? And for the moment, it was just the wet finger method to find these directions. So there is more work to do. Thank you very much.